Okay, welcome to EGR445. In today's class, we are going to talk about design of knuckle joints. So design of knuckle joints. Knuckle joint. Now what is a knuckle joint? Knuckle joint is exactly like a knuckle. So if you look at the way the knuckle joint is, you are going to have something called as the eye end, and you are going to have a fork end. So I'm going to show you the three-dimensional picture of how a knuckle joint looks. So a knuckle joint looks something like this. So this is called as the eye end. This is called as the eye end. And then here on the other side, you have sort of a forked end. So this is how the forked end is going to look like. So this is an eye end. This is the fork end. And then what we have is we have a pin that goes through the knuckle joint. So you have a pin that goes through the knuckle joint. So I'm going to just show you the pin. This pin usually has a sleeve and either a lock nut or a cotter pin. So what is the purpose of a knuckle joint? Knuckle joint is similar to cotter joint, but I want you to understand knuckle joint can allow the motion about the axis of the pin. So this is the pin axis, and then this type of motion knuckle joint is can sustain. Now what we need to do is we need to design the knuckle joint. And designing a knuckle joint means that we find out, starting from the rod dia, then we have to find out the pin dia. So I'm going to call this capital D. Then we have to find the pin dia. This is small d. Then we have to find out the external diameter of the eye end, which is D1. Then we have to find out the thickness of the eye end, which is nothing but T. Then we have to find out the thickness of the fork end, which I'm going to call T1. Then we have to find the bearing stress, make sure that the pin safe for bearing. So what we are going to do is we are going to use the design principles and design equations that we used earlier to find out the principal dimensions of the knuckle joint. And knuckle joint is commonly used in lots of applications. And you may not see the knuckle joint as this big joint with eye end and fork end. But the manifestation of knuckle joints are everywhere. For an example, a simple case would be look at the chain. So if you look at the chain link structure is something similar to that of the knuckle joint. So you have a pin, you have an eye end, you have a fork end. If you look at the bearing that is supported, it also has something similar to a knuckle joint. If you look at the light pole, and I just want to show you, for example, if you have a light pole or a pole that is used to carry electrical current, you will have some sort of a support. And here at the end of the support, you are going to have a knuckle joint. That knuckle joint, so this is the pole, this is the cable, and this is the knuckle joint. So there are lots and lots of applications of knuckle joints. A simple pin joint can be considered as a knuckle joint. So what we are going to do is we are going to design this knuckle joint step by step, and then we will check if the knuckle joint is safe under different loadings. So when the question is design a knuckle joint, what they will do is they will give you the value of the load. So load P in kilonewtons will be known. Then the material for the knuckle joint will be known. Material will be known. So what it means is the value of sigma T, which is the tensile stress or tensile strength, sigma C, which is the compressive strength, and shear strength will be given to you. And what we need to do is we need to look at the different resisting areas and use the equation for stresses. And just like cotter joint, we have to design the knuckle joint. Now what I'm going to do is I'm going to, just like cotter joint, I'm going to give you a step-by-step recipe for the knuckle joint. So what you can do is you can plug in the values of P, and then you can substitute the values of sigma T, sigma C, and tau, and then you can find out the dimensions. So what we will do is we will start with step-by-step technique. One thing I just want to tell you that there are different ways a component can be designed. So one classic way a component can be designed is they identify a principal dimension. For an example, in the case of cotter joints or knuckle joint, this diameter D is considered as a principal dimension, and all other dimensions are expressed in terms of this principal dimension. And usually the other dimensions have some sort of empirical relationship with the principal dimension. So there are two ways a problem can be solved. First and foremost, you can find important dimensions using empirical relations and then check that the joint or the component is safe. This is one way of solving the problem. So for an example, if you look at the textbook, in the textbook, they give the, the diagram, the sketch for the quarter joint, they give the sketch for the knuckle joint, and they specify the dimensions in terms of a principal dimension. And then once you know the principal dimension, all the dimensions are known. You can draw the joint, you can analyze the joint, but what we need to do is we need to make sure that the system is safe under the prescribed load. The other approach is starting from the basic. So what you do is you start with equation stress is equal to load divided by area, or tau is equal to load divided by area. You know the values of stresses. So this is given to you. This is given to you. External load is given to you. You find out the areas and then decide the dimension. One thing that you want to keep in mind, that the answers that you may obtain from these two approaches may differ. But nevertheless, as an engineer, our primary objective is to make sure that the joint or the whatever component we design is safe when we operate. Also, other thing that is super important, that when you perform these engineering calculations, the idea is to get important dimensions. So there are important load bearing or stress bearing dimensions. And these important dimensions are critical just to make sure that the joint is safe. And then based on these important dimensions, you start sketching the joint and add the auxiliary dimensions that allow you to draw, check, and manufacture the joint. So please understand that what we are going to do is we are going to find out the important dimensions. And then when we start sketching, we will actually start adding additional dimensions. One potential example here is this fillet radius that you observe here. This fillet radius that you observe here. We don't find this fillet radius dimension directly from the equation. But what we do is, based on the empirical analysis, we provide a fillet radius of 3 or 4 millimeter so that there is no stress concentration. Okay, any questions at this point? If there are no questions, we will start the design of the knuckle joint step by step. So step number 1, determine rod dia. And the dimension for the rod diameter, I'm going to say it is capital D. The failure is in tension. So I'm going to assume tensile failure. Sigma T that is given to us, that is P divided by A, which is equal to P divided by pi by 4 D square. In this problem, external load is given, sigma t is given, the only unknown is the value of D, and that value can be found out. So this is the cross-sectional area or the resisting area that you need to design. One thing that I just want to clarify, that if you get the areas and the dimension in fractions, always round it up to a higher side. Say for an example, if your dimension is 23.4, then make it 24, because nobody is gonna make a joint with rod diameter as 23.4. You will start with preferred numbers and standard dimensions that are available for purchase at a commercial off-the-shelf part or a catalog item. The next step is step 2 is determination of pin diameter. Determination of pin diameter. Now, please understand, this is something similar to the problem that was assigned in the first homework. So we had a joint, something like this. This is not exactly knuckle joint, but has the structure or the loading of a knuckle joint. So this was the joint, and there was a pin at the center. Now this pin would fail at two locations. It can fail over here, it can fail over here. So basically the pin, so this pin is in double shear. So if you apply load P, the pin is going to fail in double shear. So what we are going to do is, we want to find out the diameter D. Tau is equal to P divided by pi by 4. I just have to be consistent. D square, this is capital D, T square, and from here we can find out the diameter of the pin. Now, one thing I want to tell you, that the diameter of the pin that we are gonna get from this equation can be used for further analysis, but it is customary to modify this diameter. So we modify pin diameter so that pin is stronger in bending. Because otherwise, what may happen is we would determine the value of the pin diameter, recognize that pin diameter dictates the inner diameter of the eye and inner diameter of the fork. So for some reason, later in the calculations, we find out that if our pin is not safe in bending, that means we have to go back and redesign the joint. And that's okay if we have a lot of time. But its practice is customary to increase or to change the value of the pin diameter so that the pin is safe in bending. So what we do is we approximate this small d is equal to capital D. So the pin diameter is equal to rod diameter, and that can be used for further calculations. Now, one thing I missed here is there is 2 because the pin is in double shear. So when you find out the value of the pin diameter D, you will observe that usually this D is less than capital D. But what we do is, so that our pin is safe in bending, we sort of increase the diameter of the pin so that when under the load, when the pin is bent, it can support the bending stresses. And that is an important step that avoids the reiteration of the design calculations. Any questions? Next step, step 3. Now please note, once we know, yeah, do you have a question, Kaden? Okay, let me just raise your hand and I will unmute you. Okay, Kaden, you're unmuted.
Yeah, so if we are going to increase the pin diameter to the same diameter as the rod, is there ever a case where it would need to be larger for the shear stress? Or like, could we just kind of skip to making it the same diameter as the rod?
All right, so let's think about this design. So please notice that this small d will be calculated based on the twice of area because the pin is going to be in double shear. Typically, the tensile to shear ratio is about half. So if you have about tensile stress, which is about 70 to 65 Newton per millimeter square, the typical shear stresses are in the range of 40 to 45 Newton per millimeter square. So basically, the diameter small d that you calculate with those stress relationships is going to be less than capital D. And you can actually plug in the values. It's very easy to do. Substitute tau is equal to sigma t divided by 2 and find out the value of D, and you will realize that the value of D, what you are going to get, will be most likely less than capital D. So that's why we usually take the pin diameter is equal to rod diameter. And in a case, I haven't seen a case where pin diameter is larger than the rod diameter, but I have seen the cases wherein the knuckle joint is subjected to a fluctuating load or sort of a fatigue load. In that case, sometimes the material for the pin is changed. So what happens is you could have the cotter joint that is made up with cast iron, but you make the pin maybe out of mild steel. So I have seen the case when the dimensions are typically kept the same, but we change the material for that particular subcomponent. Does that answer your question? Okay. So does anyone else have any question? You are welcome to use the chat window or just raise your hand and I will unmute you. Okay. Moving on to next step. In step number 3, we are interested in designing the eye end. And let me just draw the eye end. This is actually very simple. If you look at the eye end, what we have is we have an eye. So something like this. And there are some variations possible. So for an example, I have seen knuckle joints wherein what they do is Instead of the rectangle here, you have some sort of hexagon, or there is some variation in the shapes and size, but this is a very simple eye end design. Now, one thing I want to tell you that through the inner dimension of the eye end, the pin is gonna go. So please note, this is actually nothing but the pin diameter. So this is the diameter of the pin. So D pin. This is the internal diameter of the eye. There would be some clearance because you do not want the knuckle joint to be press fitted. If you look at the cotter joint, the cotter is hammered into the joint. So believe it or not, there is some amount of press fitting, the interference taking place when the cotter is in between in the joint. However, when you have the knuckle joint, you allow little bit of tolerance so that the pin is able to rotate. Because I want you to think about the case, what would happen if the pin is press fitted into the joint? Joint would lose the degree of freedom that is necessary. The purpose of the knuckle joint to allow slight relative motion between the eye end and the fork end. If you have a pin that is press fitted, then there won't be any degree of freedom between the eye end and the fork end. The other thing that can also be thought about is knuckle joint can be used to provide compensation for slight, and I'm saying slight misalignment, not huge, but slight misalignment. If you have the pin that is press fitted, you do not get that misalignment advantage. But a word of caution, you don't want that pin to be too loose. Otherwise, what would happen is every time the load is transferred, the pin is going to hit in the eye end and in the fork end, and basically it would cause surface stresses and some sort of pitting and damage to the pin. So inside dimension of the eye is the diameter of the pin. Now, what I want to tell you here is this is another empirical relationship that you should always keep in mind. Whenever you have a joint that has an internal hole and external boss, this shape is called as the boss. So if you have, and you would see this type of shape in lot of applications. Say for example, you would see this in something like called as plumber block, or you would see this in some sort of bearing support. You will see this in some sort of rod support. So whenever you have shape like this, wherein you have an internal hole, and I'm going to call this internal hole as small diameter D, and you have an extra, yeah. So typically, half a millimeter to 1 millimeter hole, clearance is good. So, and then what you, if you have an external circle, something like this, please note this typically is 2 times the internal diameter. And here is a reason for this 2 times the internal diameter relationship. Now understand that the common failure mode for a structure like this, there are 2 ways this structure can fail. So this structure can fail horizontally, and what I mean by horizontally is this top part sort of separates out from the bottom part. So top part separates out from the bottom part. And then this is how the structure could fail. And the second way this can fail is this portion actually comes out. So what happens is basically that this top part actually comes out. And when we are going to design the joint, when we are going to design the knuckle joint, we will look at these types of failures. However, there are some additional failures that are possible. So what happens is, so just want to show you something like this. So there are some additional failures that are possible. So there could be some type of rubbing somewhere over here. There could be additional surface stresses, because usually whenever you have a boss and an internal hole, you have a shaft or a bearing or some other rotating or some other moving component going through. Either this could be rotating or this could be translating or could be both. So this joint, there is possibility of high stress concentration where the contact is taking place. And to be on the safer side, based on the experiments and properties of the steel and other materials that are commonly used, if you use the outside diameter as 2 times the internal diameter, the system design is going to be safe. So this is an empirical relationship that I would strongly recommend that you remember if you want to design a structure or a system, something like this, that has an external boss and an internal pin. The diameter of the boss should be at least 2 times the diameter of the pin. And if you want to take a look at this, just see the chain link. You are welcome to look at the chain link. You will observe that the chain link has an internal hole and chain link has an external boss. And there is a pin that is holding 2 links together. So this external dimension, this external diameter is typically 2 times of internal diameter. So 2 times the internal diameter. This is a common guideline. And I have seen the outside boss diameter slightly bigger than the pin diameter when you don't predict or you don't have a good understanding of what type of loads are going to be on the pin. So for an example, if you are trying to design a connecting rod and a crankshaft assembly, where you know that the loading is sort of a fatigue loading, there is continuously varying load, the temperature is high, you may have lubrication, sometimes you may not have lubrication. So in that case, you can increase that boss diameter, but you have to make sure that when you are designing for the regular operations or regular applications, that the boss diameter is typically 2 times the pin diameter. So here is what we are going to do. We are going to assume external diameter, the external is equal to 2 times the pin diameter. And please note, we already modified our pin diameter to the rod diameter. So this is the pin diameter. And so this is the rod diameter. So our external diameter is going to be 2 times the rod diameter. So I just want to tell you that this is D. I'm going to call this D pin is equal to D rod. Now, what we need to do is we have to look at the way this eye could fail. And this failure mode will tell us the thickness of the eye end. So what I'm going to do is I'm going to say this is the thickness of the eye end. This is T. And I just showed you the two failure modes. So what I'm going to do is I'm going to look at the first failure mode, wherein the eye end gets failed in tension. So, and I will show you how that failure is going to look like. So this is the eye end. And this eye end will fail in pure tension. So this is how eye end would fail. This is the resisting area. And if you want to find out the resisting area, these are the dimensions. This is the external diameter, which is 2 times diameter. This is the internal diameter, that is D. And what I want to do is I want to use these two dimensions to find out the thickness. So considering tensile failure, sigma T is equal to P divided by area. P divided by area is 2 times D minus D multiplied by T. Now in this problem, external load is given to us, then the design stress is given to us. We already know the value of diameter. So the only unknown in this equation is value of thickness. So here we can find out the value of thickness. However, what we need to do is we need to check if this thickness is good to support the shear failure. So next step is step 4. Checking eye end for shear. And let me just show you how that failure could happen. So if you look at the way it's going to fail, this is how it would fail. And the area that is resisting this failure is on this side, and the same failure area is going to be on this side. And the piece that should come out will be something like this. And this is the failure area. Now I want you to understand that this is the shear failure. And why is this a shear failure? Because look at the area. Area is parallel to the line of action of force. But one thing I want you to note that we already know all these dimensions. So this dimension, that is T, we determined from step 3. The inner diameter and outer diameter is known. So I want to show you. So just check this out. From here to here, that is outer diameter by 2. Here to here, that is going to be inner diameter by 2. So which means the difference here is going to be dO minus di divided by 2. So that is the one side of the area. This other side of the area is T. And now what we need to do is, please note that there are two areas on either side. So this actually is in double shear, and I have to write this down. So this is in double shear. So tau is equal to P divided by 2 times T multiplied by dO minus di divided by 2. And I'm going to simplify this equation. We already know that the inner diameter is capital D 2 times T. Inner diameter is capital D. Outer diameter is 2 times the inner diameter divided by 2. So this equation is half gets cancelled, and you have T times D is equal to tau. Now, a word of caution. Now, I want you to quickly compare the equation given in step 3 and equation found in step 4. In step 3, we also have, if you believe, just let me substitute here, is nothing but P divided by D times T. And if you look at in step 4, we have the same equation. So if you look at the way we are going to find out the dimension, usually the shear stress, which is tau, is less than sigma T, which is less than sigma C. So this is shear strength, this is shear, this is tensile, and this is compressive. So what it means is, if you find out the value of T from step 3, most likely in step 4, your joint will fail. So it might be a good idea. It might be a good idea to revise the dimension in step 4. So what I'm trying to say here is, you can find out the dimension for T from step 3. You can find out the dimension for T from step 4. And out of these two dimensions, select the larger dimension. Select larger T. So you'll obtain 1T from step 3 and step 4. So out of these two, you will use the larger dimension. Any questions here? Now, next thing that I want to talk about real quick is checking pin for bearing. So step 5 is checking pin for bearing. Now I want you to look at the way this joint is going to rub or bear on the pin. So if you have an eye end and if you have a fork end, I'm just going to show you the eye end. So at this point, the thickness, the inner diameter, outer diameter of the eye end is known. And what's going to happen is the pin is going to go down through this eye end. So what's going to happen is part of the pin that is resting against the surface, the inner surface of the eye, would be continuously rubbing. So what we need to do is we need to check pin for the bearing, and I'm going to say in the eye. Similar bearing is possible in the fork end, but please try to understand the fork end thickness is usually greater than the eye end thickness. What it means, if the pin is safe in the bearing when it is in the eye end, it usually is safe in the fork end. And in the last class, we talked about the bearing stress. Sigma B is equal to P divided by D, which is the diameter of the pin, multiplied by the thickness of the eye. Because if you look at the projected area, and I'm going to show you the projected area here. If you look at the projected area is something like this. So this dimension is T and this dimension is capital D, as the diameter of the pin is equal to the diameter of the rod. So this dimension, you'll change this to P D times T. And what you need to do is you have to make sure that this bearing stress is less than the design bearing stress. Now here is something I just want to point out. Believe it or not, we are using the exact same denominator for last three equations. So let's quickly go through what we are looking at. So if you look at step 3, I want you to look at this denominator. If you look at step 4, you are looking at this denominator. And in step 5, you are also looking at the same denominator. Typically, the bearing stresses are greater than the shear stresses. So let me show you. Tau is less than sigma B. So most likely, the design is going to be safe. Because in the earlier case, in step 4, we are finding out the value of T using the shear stress. That shear stress is less than the bearing stress. That gives us slightly higher diameter, a higher thickness, which means in this case, checking pin for the bearing is usually a customary. It's always going to be safe. Okay, now this finishes the critical dimension determination for the eye end. Now there is something else. Sometimes what you do is, depending upon what textbook you use, sometimes they consider the tensile failure of this end here and find out the dimensions. I'm going to call this B1 and T1. Sometimes they find this dimension B1 and T1. But the customary is, I want you to look at these dimensions are sort of the intermediate dimensions going from the rod end all the way to the eye end. So what happens is these dimensions are determined empirically. So, and what you do is, if you look at the textbook, these dimensions are given in terms of the principal diameter or the principal dimension, rod diameter. And then if you want, you can check this cross-sectional area for tensile failure. And some design books do that. Okay, any questions? Now, next step, step 6, we have to move on to the forked end. So design of fork end. Now I want you to think about the fork end. The fork end is going to look something like this. So fork end is something like this. Now, some of you may say, hey, this is exactly similar to two eye ends that are attached together. And you will be correct. So fork end is like two eye ends. So you have an eye here and you have an eye over here. The only difference is the amount of area that is available to resist the stress is much, much greater than the eye end dimension. So what happens is, whenever we look at the fork end, typically we don't check fork end for failure. And the reason for that is we already checked the eye end for failure. And if one eye end is safe in failure, if we have a fork end, that is sort of one eye on the top and one eye on the bottom, it's going to be safe. So now from manufacturing point of view, this dimension will be the thickness of the eye end, which is, I think it is T, plus some clearance. So which is usually considered T by 2 plus say 3 millimeter. And this is an empirical relationship. So depending upon the textbook that you use, you will see that this dimension may change. Sometimes I've seen using this relationship, T is equal to 0.75 times the rod end diameter. And please note, on the eye end, the rod diameter is going to remain the same, because that is exactly the same way the joint could fail. And then the other dimensions of the forked end, you can actually look at the textbook, and they will provide you with the empirical dimensions for the radius here, for the radius here, then this dimension, this dimension, these dimensions will be determined from empirical relationship. Okay, so any question in the fork and design? So this is how the knuckle joint can be designed. If you look at the textbook, there is additional step wherein the pin is checked for bending, which is last step, step 6. So you will find out all relevant dimensions of the forked end. Now the last step, which is step 7, is check pin for bending. Now, I would like to spend some time on how the pin can actually bend inside a knuckle joint. So let's look at the knuckle joint. Knuckle joint has an eye end. Knuckle joint has a forked end, and pin is transferring load from eye to the fork. So you have pin over here. Now imagine you have a load over here, you have a load over here. So this pin would most likely going to deform in this direction. Now what I'm going to do is I'm just going to show this pin vertically. So consider that you have this eye end and forked end, but instead of drawing them horizontal, I'm drawing them vertical. And I'm going to show the pin that is somewhere over here. Now, because of the bending of the pin, the loading on the eye end and the fork end is not going to be uniform. So what's going to happen is, if you look at the load on the pin, the load distribution on the pin will be something like this. So there will be uniformly varying load, and here there will be uniformly distributed load. If you look at the quarter joint, the quarter also was subjected to similar load variation. Now let's spend a minute on the load. You have the external load P over here. You will have the same external load P over here. So this is the same load P, same load P. What it means is, I want you to observe this very carefully, that this area plus this area is going to give me an external load P. So this area plus this area is going to be external load P. If you look at this area, this is also going to be an external load P. So if I want to find out the magnitudes of the loads, so I'm going to say, I'm going to call this P1, and I'm going to call this, say, P2. So P1 is the magnitude of uniformly varying load, and P2 is the magnitude of uniformly distributed load. Just check the length where these loads are distributed. This distance is thickness divided by 2 plus, say, 3 millimeter. This distance is thickness divided by 2 plus 3 millimeters, and this distance is thickness. And I am ignoring the clearance, but just understand this loading is how the joint will be loaded. So how do I find out the value of P2? So first and foremost, to find P1 and P2. External load P that will be given in newtons is nothing but P2 multiplied by T. Please note, value of T is already known. So from this equation, I should be able to find out the value of P2. Now look at the P1. P1 is the triangular load. So external load P is equal to the area of the triangle, which is 1/2 T by 2 plus 3 multiplied by P1. But please understand that there are two triangles. Since there are two triangles, this entire load will be multiplied by 2. And from this equation, T is known, external load P is known in Newton. I should be able to find out value of P1. So I now know the value of P1 and I know the value of P2. So what I need to do is I need to find out the maximum bending moment. One thing I want you to understand that the loading is symmetric. Loading is symmetric. So since the loading is symmetric, can someone tell me where the bending moment is going to be maximum? How would the shear force diagram look like? Where would the bending moment be maximum? Yes, the answer is correct. The bending moment in a symmetric loading is going to be maximum at the center. And what we can do is we can find out the value of the bending moment at the center, and I will just work out this. And the reason for working out this bending moment is you have similar loading in the case of quarter joint. So you have P1, and I'm going to call this dimension for the sake of simplicity T2. T2 is equal to T by 2 plus 3 millimeter. And I'm going to call this dimension as T, this dimension as T2. Now please note that the area, so one thing that I want you to understand is if you look at the center of gravity or the centroid of the triangular area, that will be somewhere over here. So this is where the total load will be concentrated. So what I'm going to do is I'm going to consider the section XX, which is at the center, and take the moment of the forces on the left hand side of section XX. So please note this force here on the left hand side is going to be T1 multiplied by T2 multiplied by 1/2. That is the magnitude of this load. And this load will act at the distance T2 by 3. So the moment given by this load, I'm going to write this down. Since this force is downwards, the moment given by the downward force is negative, is going to be minus 1/2 times P1 multiplied by T2. This is the force multiplied by the lever arm is T2 by 3 plus T by 2, because we are finding out the moments at XX. Now, then there is the second force, which is on the left hand side of this cross section, which has the magnitude uh, P2. This is P2 multiplied by, and look at the distance, how far this load is spread, which is T by 2. So this will be P2. Since it's a rectangular load or uniformly distributed load, the load is going to be P2 times T by 2. And this load will act at the centroid of this rectangular cross section. This load will act at the centroid of the cross section. And this force will be in the opposite direction. So this force is going upwards. That's why you have the positive sign, multiplied by T by 2. And this distance is 1/2 T by 2. So multiplied by 1/2. So what you can do is note that all these values are known to us. Value of P1 is known, value of P2 is known, value of T2 is known, value of T1, value of T is known. You will get value of MXX. So this moment will be known. Now look at the cross-sectional area of the pin. The pin is a circular diameter, so sigma bending is equal to M divided by I multiplied by Y. So what you will do is, you will substitute the value of MXX and make sure that the units are consistent. Since it's a circular cross section, pi by 64 times d to the power 4 multiplied by d by 2 is equal to sigma b. However, please note, we already have found out the dimension of the pin. So pin diameter is already known. So, and that is equal to capital D, which is the rod diameter. So what you will do is, in this equation, you will substitute MXX divided by pi by 64 multiplied by rod diameter to the power 4, rod diameter by 2, and find out the value of sigma b. So find this out. And this value should be less than sigma t. And that is how you will check the pin in bending. Any questions? Any questions on the design of what if it is greater than sigma t? Now, here is something that I want you to mention. It may not happen, but in case you observe that sigma b is greater than sigma t, what you can do is, there are two options at this point. First option is redesign. Now, what this redesign means is, you will have to change the internal diameter of you have to change the diameter of the pin. That will change the internal diameter of the eye. That will change the external diameter of the eye. That may change the thickness of the eye, and basically your joint will need to be redesigned. Alternatively, you can say that we will change pin material. So you would change the pin material so that uh, the, the actual bending stress is less than the design strength of the material. So both options are valid. So you can actually go back and redesign. And many a times what I have seen is if you look at the way these designs are done, uh, these formula are given or entered in Excel or some other software. And what you do is you just go back and change the dimension and you get a completely new joint. Does that answer your question, Matthew? Okay. Any other questions? So your next assignment is design of knuckle joint. I would encourage you to look at the worked out example in the textbook. Textbook has a couple of examples where the knuckle joint is worked out and shown with the appropriate dimension. So please look through that example, design your knuckle joint, and then what you can do is you can CAD the knuckle joint. SolidWorks has plugins for design of quarter joint and knuckle joint. I don't know if they are included in the regular version of SolidWorks, or you may have to pay extra to add those plugins. But or what you can do is you can actually write a simple Excel spreadsheet with all these calculations, and then you should be able to get the answers directly. Okay, 7:12, I'm gonna give you 15 minutes break and we will continue our discussion after 15 minutes. So I will be back at 7:30 and we will continue the design lesson. Now we will start with design of keys and couplings. Okay, in the next part of this lesson, we are going to talk about keys, couplings, and shafts. So design of shafts, keys, and couplings. Now, we talked about shafts. So consider that if you have an engine, say if you have an engine or an electric motor, it has a shaft coming out. This is the rotor shaft. And then you have a pump. So maybe a centrifugal pump or some sort of reciprocating pump. And what we need to do is we need to attach the motor shaft to the pump shaft. So this is the motor shaft. This is the motor shaft. To the pump shaft. Now, in this particular example, I'm not going to talk about any change of speed. So for example, if the motor is running at 1200 RPM, the pump will also rotate at 1200 RPM. So what I want to do is I want to have some sort of shaft that connects these two shafts. Motor shaft is connected to the pump shaft. Now, clearly, we can't just take a shaft and weld it to the motor shaft and weld it onto the pump shaft. So what we need is we need some way to attach this motor shaft to an intermediate shaft. So I'm going to call this an intermediate shaft. And then this intermediate shaft all the way to the pump shaft. Clearly, we don't want this, the shaft which is in between, to be hanging just like that. We want it to be supported, so there will be some bearings. And depending upon the amount of deflection, loads, the distance, you will have a number of supports. The other thing which is important is many a times the center line of the motor shaft and the center line of the pump shaft may not be perfectly aligned. So there are issues. First and foremost, we want torque to be transmitted from motor to pump. Secondly, there could be some misalignment. Now, there are two types of misalignments possible. So you could have an angular misalignment, and I'm going to show you an exaggerated view. So you could have a completely angular misalignment. So there is an angular misalignment, or there could be a, a sort of a translational or offset misalignment. And we want to make sure that whatever coupling that we use to attach these shafts is somehow is capable of taking into account the angular and offset misalignment. Otherwise, what would happen is there would be unnecessary vibration, there will be unbalance, excessive load, and that will lead to premature failure. We want to avoid that. The other thing that you want to make sure that when the prime mover, which is the motor, is going to start pump, there could be potential overload. So there could be potential overload. And we want our design to compensate for this potential overload. And this potential overload can happen just by surge in the initial torque. So for an example, you would notice that as the motor gets attached to the pump and is loaded, there is all of a sudden increase in the torque, and then sort of torque kind of stabilizes. So there is this initial surge in the torque, which is called as T initial. We want our the transmission to take care of this initial surge. Now, what that means is sometimes that will lead to additional twisting. So excessive twisting. And you don't want the shaft to break. In a sense, you want this shaft to act as a torsional spring wherein it is capable of absorbing these sudden shocks in the power transmission and somehow smoothen the power transmission. So whenever you have a coupling is used to compensate for the misalignment, to compensate for potential overload, and sometimes the coupling is also used to dampen the vibrations. And there are different types of couplings. But I just want to, before we talk about couplings, let's talk about how these two shafts are attached. If you look at a motor shaft, and I'm going to show you a motor shaft here, you would observe that the motor shaft has a keyway. So basically, you have this motor shaft, and in the motor shaft, usually what happens is you have a keyway that is cut. So you would observe so this is basically the keyway that is cut in the motor shaft. I'm just going to show you a section of the motor shaft. And what happens is the other shaft is attached somehow. And then what you have is you have one key, one single key that attaches or connects the first shaft to the second shaft. So let me show you the side view. If you look at one shaft, which is on the left-hand side, and you have the other shaft on the right-hand side, there is a keyway, and through this keyway, there is one single key that is used for power transmission. So the way the power is transmitted is shaft number 1 transmits the torque. The torque causes force acting on the key. That force gets transmitted to the second shaft, and with that force, you have torque on shaft number 2. Now, this key plays an important role. So, key is a power transmission element, and this is also like a mechanical fuse. So, this is like a mechanical fuse. So, in the case of electrical fuse, if the current exceeds the power transmission capability, what happens is excessive resistance and heat they are generated, and because of that the fuse melts. Just like that, if the power transmission exceeds the design capabilities of the transmission, then most likely the key is going to break. And once the key is broken, then you will observe that the drive shaft, so I'm going to call this a drive shaft, and this is the driven shaft, they separate. And that is sometimes deliberate to make sure that we do not overload the prime mover or overload the drive, or we protect the equipment if there is something wrong with the drive. And there are different ways these keys could be designed. So for an example, you could have a square key. You have a square key. You could have a rectangular key. There could be a Woodruff key. And there are many key designs that are used in industry. And depending upon the application, depending upon the amount of space that is available, depending upon the amount of power transmission, amount of fail safe that you need, different keys are used. And for a theoretical background, I would encourage you to look at the textbook. In the textbook, there are pictures of different types of keys, and their potential applications. Many a times, keys are just held in place because of the geometry. So for example, if there is not much of misalignment, the shaft, drive shaft and driven shaft are perfectly aligned, then you can just have a key and maybe some sort of a sleeve coupling over the key that would help you with the power transmission. Sometimes you expect there could be some vibrations and there could be some shocks, and at that time you want that key to be secured to the drive shaft or the driven shaft. So you can see some sort of screws, or you can add a set screw or some other component that would hold that key in place. Now, what we are going to do is we are going to look at the way the key can fail. So what are the different ways a key could fail? Key could potentially be crushed in the shaft. So just think about it. Key could be crushed in the shaft. Key could be sheared in the shaft. And we want to make sure that this small rectangular piece that we are going to design, or small square piece that we are going to design, is safe in crushing and in shear. Now, even though we have designed shafts, one thing that we did not consider when we are designing the shafts is the effect of key weakening. Now, please observe here that if you have a solid circular shaft, when we are designing shaft, we always assume that the shaft is solid and circular. So we assume the shaft is solid and circular. But recognize that as soon as you add keyway, as soon as you cut a key, the shaft is actually weakened. And somehow we have to compensate this key weakening effect. So as soon as you cut the key, as key is cut, shaft weakens. And the weakening of shaft not only in section modulus, but I want you to observe that this key actually has these sharp corners. So basically, not only the section of the shaft is weakened, but the stress concentration may also occur. So it is very difficult to account for these two effects and to use some practical techniques to actually find out. So in certain cases, what we do is we resort to some approximate techniques. So what we do is, once we design shaft, say if you look at the design procedure for shaft, assuming the power is given as 2 pi nt divided by 60. So power is known, speed is known. So we can find out the value of torque. And this torque, once the torque is known, we are going to use the fundamental equation of torsion, which is tau is equal to T divided by J multiplied by R. And for the sake of discussion, let's assume the value of J, it's a solid circular shaft, so pi by 32 d to the power 4, and R is equal to d by 2. So what we do is, at the end of the day, from this equation, we will find value of diameter. However, for practical purposes, we are going to cut the key, and that key is going to give rise to some stress concentration. So to compensate for key weakening effect, what we do is we slightly make this shaft bigger to account for key weakening. We change the diameter by 1.1 times diameter to 1.2 times diameter. And that is to compensate for the weakening that is going to take place because of the key. And once that step is taken care of, then what we can do is we can look at the design of key. So what I want to show you is, let's identify the forces that are acting on the key. If you look at the key, we can design a square key where the cross-sectional area is square. So this dimension, thickness, it's same as the width. Or you can have a rectangular key wherein you can have width and you can have thickness. Design procedure for both the keys is same, and additional dimension in the case of keys is nothing but the length of the key. So when we design the key, this is the length of the key. So we have to find out the width, thickness, and length. So that is the purpose of key design. And let's look at, when we have a key inside the shaft, let's look at what type of failures are possible in the key. So if you look at the key, I'm just going to show you the key. Please note, half of the key is going to be in the shaft. So half of the key, let me make a bigger shaft here. Half of the key is going to be in the shaft and half of the key is going to be in the coupling. So this is how the shaft is going to look like. So I want you to observe the area that is going to get sheared when the shaft is going to rotate. So if this is the torque that is acting, then the force on the key, is going to be torque divided by the radius of the shaft. R is equal to radius of the shaft. And if you look at the way the key will be sheared, key is going to get sheared around on this plane. So this is the cross-sectional area of the key that will get sheared. This is the shear failure. And this shear failure, if you look at the shear failure, the dimensions are, and I'm just for the sake of discussion, I'm going to use a circular, I'm going to use a rectangular square key. If this dimension is T, the resisting area is equal to T times L. That is the area that is going to resist the shear. Now, the next thing is look at the crushing failure of the key. So next thing that is possible is crushing failure of key. So same key. So we have this key. Half of the key is inside the shaft and half of the key is inside the coupling. So this is how the key is going to look like. If you look at the area that is getting crushed, this is the area that is getting crushed. And this area is nothing but if this is dimension t, assuming the square key, this dimension is t, the area crushing is equal to T by 2 multiplied by L. Now, as you can see that there are two types of failures possible in key. So sigma C, which is crushing, is equal to P divided by T by 2 times L. So what we can do is we can design the key for shear and check the key for crushing, or we can design the key for crushing and check the key for shear. So both approaches are valid. So what we will do is we'll design key for shear and check it for crushing. So let me take an example, a simple example. And it is customary to assume the dimension of key to be anywhere between d by 4 to d by 6, where d is the diameter of shaft. So there are design rules. Based on the design rules, what we do is we find out the preliminary dimension of key, and then what we do is we basically modify the design if key fails in either shear or in crushing. Okay, before I proceed, I just want to make sure that we are clear about the design of key. And what I'm going to do is I'm going to take a very simple example as an exercise. So problem. Design a rectangular key for 50 millimeter diameter shaft. The shearing and crushing strength are 42 Newton per millimeter square and 70 Newton per millimeter square. Same material is used for shaft and key, and ignore key weakening effect. So in this problem, we have to design a rectangular key, and the diameter of the shaft is 50 millimeters. The shaft and the key is made up with the same material, and we have to find out the width, thickness, and the length of this key. Since it's a rectangular key, I'm going to assume following dimensions. I'm going to assume that one dimension of the key is d by 4, and this is a standard dimension, and the other dimension is d by 6. So you have d by 4, the other dimension is d by 6, and this is the length of the key. Now, first and foremost thing is the shaft diameter is given to us. However, if you look at this problem, the value of torque is not known. So we cannot find out the forces that are acting on the key. So how do we find out the value of torque that can be transmitted by the shaft? One thing to observe, that the shearing and crushing strength for the shaft and the key are already given. So what I'm going to do is I can find out maximum torque transmission capability of shaft is equal to tau is equal to T divided by J multiplied by R, where tau is equal to 42. I have T, J, it's a circular shaft and it's a solid circular shaft, pi by 32 multiplied by 50 to the power 4 multiplied by 50 by 2. That will give me the value of torque. And this torque is the maximum possible torque that this shaft can transmit. And clearly, this would be the maximum torque that will be acting on this key. So once you find out this value, I will give you my answer, but please check it. The answer I got is 1030.8 Newton meter. So this is the max torque this shaft is capable of transmitting before it fails in shear. So what I would do is, now I would assume the shear failure of key. And when I see the shear failure of key, this is d by 6. So this dimension will be assumed as 50 by 6. And this dimension I'm going to assume as 50 by 4. So what I need to do is find out the length of the key. So considering the shear failure of key, considering shear failure of key, tau is equal to P divided by area. Tau is 42. P is the force. The force is torque divided by radius of shaft divided by the area is going to be d by 6 multiplied by L. So which is d by 6 multiplied by L. Because please understand the shearing area is this area. Shearing area is this area. So the torque we already know 1030.8. This I will convert that into Newton millimeter divided by the radius of shaft is 25 millimeter. D by 6 is 50 by 6 multiplied by L is equal to 42, and that should give me the value of L. And my answer for value of L is 140 millimeter. But I would recommend please check this answer. So this gives me the value of L. The next thing is consider crushing failure of key. Sigma is equal to P divided by A. So sigma is equal to the load is going to remain same 1030.8 multiplied by 10 to the power 3 by 25. However, please note, since this is a rectangular key, this dimension is different. Look at the dimensions that we have assumed. This dimension is D by 4. And the crushing area is going to be 1/2 D by 4 multiplied by L. So in the next step, I'm going to substitute the value divided by 0.5 times 50 by multiplied by 4 multiplied by 140. And you can check this value, and this should be the crushing strength design. And yeah, crushing strength, and this has to be less than 70 Newton per millimeter square. Everybody understood this problem? If you have a rectangular key, the procedure is also exactly same. Square key, it's actually simpler because both the dimensions are going to be the same dimensions. Any questions on key design? Okay, now let's talk about the design of couplings. Design of couplings. So there are different types of couplings. And the most common couplings that you will see is a simple muff coupling, or also called as the sleeve coupling. So you could have a muff or sleeve coupling. The second design, which is quite common, is called as the flange coupling. So how does a simple muff or the sleeve coupling looks like? As the word says, it's a sleeve. So what you have is, you have one shaft, then you have the driven shaft. So you have driving shaft, you have the driven shaft, and what we have is, we have a key over here, and typically you would have, when you are connecting two shafts through a coupling, the keys are perpendicular to each other, and here you are gonna have a sleeve. So you would have a sleeve all the way from here to here. So this is shaft 1, this is shaft 2, and then this is the sleeve. This is shaft 1, this is shaft 2. Now if you look at the side view is going to look something like this. You will see a shaft, you will see a shaft, then you will see the keyway, and then you are going to see this sleeve, and this sleeve will also have a corresponding keyway. And what you do is, you place a key over here. So this is where the key is. And now, depending upon what we are trying to achieve, there are slight variations in this muff coupling. When the power transmission required is not large, if the power transmission required is small, then rather than using a key, what we do is, we can use a simple set screw that is acting as a key. So what happens is, in that particular case, you have something called as a D shaft. So you have a D shaft. So you have something called as a D shaft. And then what you do is, instead of key, what you do is you place a set screw. And this is a very common coupling that is used in 3D printers. So if you go to Innovation Hub, and if you look at all the 3D printers, the 3D printers usually have a stepper motor. The stepper motors, they usually have a D shaft. So they don't have keyway. What they have is, they have a D shaft, and there will be a coupling, a muff coupling. But this muff coupling, if you think about it, it's not a solid muff. What happens is, there are cuts in this muff. So if you look at the muff coupling that is used in 3D printers, so usually they have some sort of cuts in those muffs. And there's a reason for this. So what happens is that you have a stepper motor shaft here, and you have a lead screw to the 3D printer. So this is the stepper motor, and this is the lead screw. And this lead screw can be used to move the slide back and forth, or to raise the extruder, or to lower the extruder. What happens is there will be a set screw here, there will be a set screw here, and this set screw will attach left side of the coupling onto the D shaft on the stepper motor, and the other side of the coupling will attach to the lead screw, and you would put set screw. But I want you to observe that there are these cuts in the coupling, and the reason for these cuts is to allow for deflection. So this type of coupling, because of the compliance, so this actually acts like a spring. This acts like a spring. Because of the compliance, can compensate for slight angular and offset misalignment. Other purpose of this coupling, the slotted muff, is the stepper motor is starting, stopping, starting, stopping. It's not like there is continuous power transmission from the stepper motor to the lead screw. So what happens is the jerks and vibrations, they are absorbed by this spring type of coupling. So this coupling also acts like it dampens the oscillations or vibrations when the power transmission from the stepper motor to the lead screw is intermittent. So this is a slight variation of the sleeve or the muff coupling. Now, how do we design the muff coupling? So what we are going to do is, I'm going to give you the design process for the muff coupling, or the design steps for the muff coupling. So design of muff coupling. Step 1 is design of shaft. And when you design the shaft, the equations are the same equations. Power is equal to 2 pi nt divided by 60. Speed will be given to you. Speed known. Then power is known. You can find out the value of torque. Once you know the value of torque, you can use the equation T divided by J multiplied by R and find out the diameter of shaft. Next step is we need to modify the shaft to account for key weakening. So to modify shaft diameter for key weakening. And the new shaft diameter is going to be anywhere between 1.1 times D to 1.2 times D. Next step is we need to find out the key dimensions. So design key. And you can choose a square key, or you can choose a rectangular key, And looking at the key design procedure, following the key design procedure, you can find out the width, thickness, and length of the key. Now, one thing I want you to observe, the muff coupling is sort of the sleeve. So what you have is, you have a sleeve. The inner dimension or the inner diameter of the sleeve is equal to the diameter of the shaft. So this inner diameter, so D in, is equal to diameter of the shaft. Now, how do we find out this external diameter, which is DO? This is called as the external diameter DO. Now, one thing to observe, that this muff coupling is similar to a hollow shaft. So sleeve coupling is similar to hollow shaft. That means tau is equal to, we know the value of torque. This value of torque comes from here. We know the value of torque divided by J multiplied by R. But this J is going to be the J, or the polar moment of inertia of the hollow shaft. So this is going to be T divided by pi 32, T outside to the power 4 minus D inside to the power 4 and T outside divided by 2 is equal to tau. The only unknown in this equation is DO. So you can find out the value of DO. So these are the steps for the muff coupling design. Any questions in the design of muff couplings? Design of keys. The next coupling that I want to talk about, that is very commonly used, is called as the flange coupling. So design of flange coupling. Now I want you to try to visualize the problem with the muff coupling. Now for low power transmission, outside diameter may not be very large. But if you think about it, if as the power transmission capability goes high, as the torque transmission capability can go up, then the outside diameter of the muff coupling could be significantly large. To avoid that, what we can do is we can actually split this coupling into two halves. So we could have a left half and the right half. And that is how a flange coupling is designed. So if you look at the flange coupling, you have the shaft on the left, you have the shaft on the right, and then what we do is at the center line, we actually have two pieces of the coupling. So the coupling is actually made in two pieces. You have the left side of the coupling and you have the right side of the coupling. So if you look at the coupling would look something like this. And this coupling is very, very common. So you have the left half and then you have the right half. And usually these halves are symmetric. And what happens is you have a key over here, the left side, you have a key on the right hand side. So this is the key. Now these left side and right side of the coupling is held in pieces or held together using bolts. So you have bolts over here, nuts over here. So you have again nuts and bolts over here. And depending upon the design, you could have sort of an extended flange, or you could have these bolts inside the groove. So there could be some variations in the coupling. But this is how a simple flange coupling is designed. Now, there is one more variation possible, is what we can do is we can add a sleeve over here. So you could have a rubber sleeve over here. You could have a rubber sleeve over here. And what is the purpose of this rubber sleeve? Please note the left half of the flange coupling and the right half of the flange coupling is connected through the bolt. Now, if you have some sort of a deformable element that is in between these two halves, slight misalignment, slight vertical misalignment or slight offset can be compensated or can be absorbed by the deformation of the rubber or deformation of the soft element. So you could have a flange coupling that has a bushing. So you could have just the regular flange coupling, or you could have flange coupling with bushing. So you could have a bushing. And the purpose of that bushing is to compensate for slight misalignment. And this gives a little bit of flexibility when the power transmission, you don't know if the exact alignment will be maintained or not. So what I'm going to do is I'm going to give you the design steps for the flange coupling. Before I start, any question on the applications of flange coupling or applications of flange coupling with bushing or applications of muff coupling? If you have any questions, you can just type in the chat window or raise your hand and I will unmute you. Yeah, somebody raise hand. Yeah. Kaden, you are unmuted.
Thank you. So the muff coupling is always probably going to be lower profile if it had to be like in a tight space, but the flange coupling is likely to be stronger for higher torques, higher power transmission.
So muff coupling is nothing but sort of a sleeve, and that is used when the power and torque requirements are not large. But the flange coupling is used when there are some serious power requirements, when there is kilowatts of power that is to be transmitted from the driving shaft to the driven shaft.
Okay. Thank you.
Well, okay. So here are the design steps. Step 1, for any type of coupling, 2 steps will remain same. The first step is design of shaft, and the second step is design of key. So step 1 is design shaft. And I'm not going to write this down because we already know how to design shafts. Second step is design key. And again, you can choose a rectangular or a circular key, and then you can actually find out the dimensions of the key. So shaft design and key design is going to remain the same. Now, when it comes to determination of the dimensions of the flange, here are some important points. I want you to observe that this is called as the hub. So this circular, this cross section is actually called as the hub. And this is called as the flange thickness. So this is T, which is flange thickness. And there are bolts. So what we need to do is we need to find out the diameter of bolts. So how do we start? So let's find out. Now what I'm going to do is, this is where the coupling is actually designed. Step 3 is design of hub diameter. So I'm going to call this DH. This is DH. Now, whether you like it or not, if you think about it, DH is something similar to the Muff coupling. So what you have is basically you have sort of a Muff coupling that is forming the hub of the flange coupling. So what I can do is design hub diameter DH, and what you can do is you can use the relationship tau is equal to torque divided by pi by 32 dH to the power 4 minus d shaft to the power 4 multiplied by dH divided by 2. There is one shortcut that you could potentially take. So if you follow some design data books, they would just say dH is equal to 2 times d shaft. And please note, this is something similar to the boss diameter that we talked about when we designed the knuckle joint. And you use this relationship and find value of tau. As long as this tau is less than the design tau or design shear stress, you are safe. So that is how you will find out the hub diameter. Either way is fine. The next thing is, how would you find out the number of bolts? Now, number of bolts is basically dependent on the coupling. The minimum number of bolts is equal to 4. And you will see some guidelines depending upon the power transmission requirement. You can change this. They suggest different number of bolts depending upon the diameter of the shaft, which is associated with the power transmission capability. The number of bolts may change, but the function of the bolts is to keep the left side and the right side of flange coupling together. If you have less number of bolts, then what will happen is the diameter of the bolt would be significant. If you have more number of bolts, then you have to make sure that the coupling physically has space to place those many bolts. And then those bolts are not very close to each other. Otherwise, what will happen is uh, through the bolt holes, there will be cracks, and you want to avoid that. So usually there are some design guidelines depending upon the power transmission capability or the shaft diameter. And you are welcome to look at the textbook that provides you with some guidelines. So typically number of bolts go all the way from 4 to large couplings, they go to 12. But think about the case if you have a small coupling and you try to drill 12 holes, then those holes will be very close to each other, and then there will be stress concentration and a premature failure of the coupling. So what I'm going to assume, again, we don't know uh, the shaft size. So I'm going to assume, say, I'm using N as number of bolts. The next thing that we want to talk about is where would the bolts be placed. Now, again, there are some design guidelines on the where the bolts are. So this center is called as the PCD, or the pitch circle diameter for the bolts. So PCD. So this is the diameter at which the center line of the bolts would be drilled. And again, the relationship is typically, what you can do is dp, I'm going to call this the pitch circle diameter, PCD, is equal to dp, or the diameter of pitch circle for bolts, is typically 3 times diameter of shaft. And I want you to observe the relationship. The hub diameter is 2 times the shaft. Clearly, we want our bolts not on the hub, but outside hub. So minimum diameter is typically some diameter that is outside the diameter of the hub, with some clearance that allows us to tighten the nut. So this is the minimum dimension. So let's find out what are the forces on the bolt. Force on bolt is equal to the torque that is transmitted divided by the pitch circle diameter divided by 2 of the bolts multiplied by number of bolts. So this is the dp, and this is the number of bolts. That gives me the force on the bolt. If you look at the failure of the bolt is going to be because of the shear. So I'm going to call this PB. So PB divided by pi by 4 multiplied by diameter of bolt square. Now, the material for the bolt you can choose, usually steel, And the value of dB can be found out from this equation. Once you know the bolt diameter, I want you to understand there are two types of diameters whenever you design bolt. And we will talk about it in detail. So I want you to observe that the bolt actually, or the nut, if you look at the nut and bolt assembly, it is something like this. So what you have is, you have something called as the core diameter, and you have something called as the outside diameter. So it's going to look something like this. So you have a core diameter, DC is the core diameter, and you have DO, which is called as the outside diameter. This dB is nothing but the core diameter, because core diameter is the smallest area the bolt has. So this is the bolt core diameter. Now, if you want to find out the failure, if you want to find out the thickness of the flange, now for that what we need to do is, we need to look at the failure of the flange. So let me show you. The last element is flange thickness. So if you look at the flange, what could happen is, the hub, this is the hub, this is the shaft, the hub could separate out from flange. So what could happen is, basically the hub could separate out from flange, and this is nothing but circumferential shear. So the way we find out the flange thickness is tau is equal to the force, which is torque, divided by d hub divided by 2 divided by pi times d hub multiplied by t, where t is the thickness of the flange. There is an alternate way of finding out flange thickness that considers crushing of bolt. So there is an alternate way. So you can find out crushing of bolt in flange. And the way it actually occurs is, I just want to show you. This is the coupling, the left side. The bolt is here. And what happens is, this area of the bolt can get crushed. So this thickness is T, and this is the diameter of the bolt, which is dB. So what you do is, force in bolt. So please note, this is nothing but PB that already found out. Sigma C is equal to PB divided by T multiplied by the diameter of the bolt, dB. And then you can find out the value of T. And what you do is, out of these two values, you will take the maximum value. You can find out the flange thickness using the circumferential shear, which means the flange has actually come out. The bolt actually held the flange together to the other side. So basically, but on the one side, the hub started rotating in the flange. So this is the shaft. This is hub, and that got separated from the flange. So you can find out the flange thickness either from the circumferential shear, or you can find out from the crushing of the bolt, and then choose the value of T that is the maximum. This is how you will be able to design the, the couplings. So in today's class, we covered a lot of material. We talked about the knuckle joint design. We talked about the key design. We talked about the muff coupling design. We talked about the flange coupling design. And please note the examples for these are given in the textbook. I would encourage you to look at the worked out problems, follow them through, and then do the homework and the quiz problems. I'm going to stop here today, and I would be happy to answer any questions you may have.